Yeah, so.
The video comment, what do you think of video?
Biochem probably, maybe.
It's one of my favorite pictures in the book. It's such an amazing. it's
Like, I want to go climb the crystals. Like,
yeah, you can't anymore.
Oh, I know.
It's a shame.
All right. So slowly we start to see everybody coming back. Laura's back to full swing, right? Is Joe still out or?
It may be out.
Is he? Okay, all right. So we're in the home stretch here for Gen Chem also. We've only got a couple, basically what, 3 weeks left, right, before Thanksgiving is what it is? Right, so we got an exam coming up, what, 2 weeks from now, is that what it is? That sounds about right.
2 weeks from today.
Yeah.
So wait, we have like we have a lab tomorrow, right? And then no lab next week, and then an exam the week after that, or?
Well, I think it's lab and exam and then your pizza party. I don't know. What do you guys have? Something like that.
I have no idea what's happening.
Well, I mean, what I always say is check the syllabus, right? The syllabus has got the schedule for that laid out for you guys. There always is. Yep. Yeah.
So exam 3, you like had like the sections. So is it like over everything, or is that supposed to be for example?
I'm sorry. I quite.
Exam 3, you put out like an announcement that said it was like over chapters 1 through 7, and then 8 and 9 or something.
And 12.
Did I post that to the wrong?
Yeah.
Okay, I'm sorry. That should have been for my OChem. I was like, well, I don't post that for you guys. Okay, thank you. I sent that to the wrong class here. Let me go fix that. I apologize for that. I did not mean for that to be.
People were confused. Like,
Yeah,
we haven't
sorry.
done chapter 12.
Sorry, that's chapter. We are doing parts of chapter 11 though, which I'll point out when we get to that. But I apologize. I'll have to
But
go
will
delete
like
that.
it won't be like cumulative on the 3rd exam, but it will be like the final.
Sure, but I mean, there's obviously things we can't ignore from the first couple of chapters either, right? You know, but it's one of these things where it'll be obviously more focused on the recent stuff. But I will correct that and I will post to you guys exactly what we're going through. But yeah, thank you for letting me know. Otherwise, I would not have would not have realized at all. Yeah, what's up?
Is that exam going to be online also?
Yeah. We'll do it not in lab there. But I think that's fine. What was I going to say though? So, aside from me posting pointless incorrect announcements, looks like we've got a kind of a busy schedule for the next couple of weeks. So, we'll be wrapping up the molecular geometry chapter here. The next thing we're going to go into is the idea of polarity, and polarity is going to be built off of the tail end of knowing your geometries. Okay, so it's a stepwise process to be able to figure out your polarity. And again, it's one of those things where it's such a core important idea. And I try and emphasize this for you guys, and I'm not pointing fingers or blood, right? And I emphasize this, and it's really important to understand the polarity, where negatives and positives and all these things are. And then we kind of ignore it in the second semester of Gen Chem, and then it comes back in OChem and in Biochem also, right? So it is one of these ideas where I was just talking with another student that they're signing up for OChem and all these kind of things, and what should I prepare for, and all these. And I was like, well, just make sure you know all of Gen Chem 1, right? And then make sure you know all of Gen Chem 2. So as I tell all of my students, all I expect you to do is to know everything, right? Does that seem all right? Just one thing. If you know everything, then you'll be fine. Is that okay? All right, no. But the reason why I try and point this stuff out for you guys is because I know a lot of you guys are going to go on to OChem. And the first half of OChem is me just teaching you guys all the stuff from Gen Chem again. So if you guys are diligent and you're keeping your notes and all this kind of stuff, it'd be good stuff to kind of review over the summer before you guys come back for the first kind of couple of chapters there. Okay. And for those of you guys who aren't going on to OChem, that's fine too. You know, there's a big variety of you guys in here, right? But anyway, just as kind of a summary then, we were going through and we learned how to draw our tetrahedrons, and I think we had a couple of examples that we walked through there. Although not every example we did was a tetrahedron, was it? Right? I believe there was the last one there that we walked through that was a trigonal planar.
I still don't understand what's going on that one.
Okay.
Are we going through them? please tell me now.
If I remember which ones I gave you, sure. I forgot the examples, but we'll pull it back up here in just a second, right? But anyway, so make sure that you guys can draw these. Of course, this is going to be exactly the type of question that you guys expect to see on the exam, right? Draw me the geometry of this molecule, right? Tell me what the angles are, where are the lone pairs, you know, this kind of stuff, okay? You can expect quite a few questions of that kind of concept to show up, okay? All right, so I think that's kind of all the, let's say, you know, note-taking secretarial stuff we had to chat about. So let's start out with prayer then, and then we'll continue on and we'll go and look at those examples. But Lord, we just thank you yet again for another day, and just another blessing, Lord, an undeserved blessing in many ways. And Lord, we just pray that we don't squander the resources and the gifts that you've given us, Lord. Help us to be good stewards of everything that you've put before us, Lord. Just put that weight on our hearts, Lord, just to carry out the tasks that you would have us do, Lord. The things that you turn our eyes towards and the things that you want us to walk towards, Lord. We just pray for the people around us, and we pray for our families, and we pray for our friends, and we just pray for everybody today, Lord, just to take a step closer to you in whatever way that might be, Lord. And if we can reflect your light into somebody's life today, we just pray that we can be that beacon for you, Lord. We just pray to be good and faithful servants in everything. And we ask this in your name. Amen. All right. So, all right. We were going through and learning about the tetrahedrons and the shapes and the wedges and the dashes and all that kind of stuff. Where were the examples that we did? That's me torturing my OChem students.
We had,
Let's see, where was it? Somewhere around here.
we had,
There it is. Let me clean this up here some. You see, there's my very scientific notes for my OChem students, right? Magic happens. So don't worry, you guys will learn all about that when we get there.
I'm already afraid.
It's all good. It's all good. Like I said, all you gotta know for OChem is everything, right? So here's the examples that we were working through. Hopefully you guys spend a little bit of time just finishing those up and seeing if you guys can come up with the drawing the proper tetrahedrons and convincing yourself that you can draw the proper tetrahedron, checking your formal charges, making sure the lone pairs are there. If there is a formal charge, making sure you're explicit with how you show it, right? Make sure that you do show your formal charges in your Lewis structures, okay? This is maybe a little bit of a, how do I want to put this? A difference that I have with the textbook, right? The textbook just kind of, they put stuff in brackets and put it around there. Go ahead and get in the habit of putting your formal charges where you guys find them, right? I promise that'll help you guys out along the way, okay? Knowing where your negatives are, knowing where your positives are, and all this kind of stuff is going to be useful in many, many, many different applications, okay? All right, so moving our way down here, right? We've got CCl3H, okay? I'm going to skip a couple steps here in terms of counting my Lewis structures and all that kind of stuff. Hopefully you guys will not skip those steps. Make sure that you guys always get it correct.
Doc,
What's up?
there aren't that many electrons.
I would disagree with that. So 7, right, 21 plus 1, so 28 plus 4, 32.
No,
No?
because there's 3 points, I came out.
21, 26, did I just count something wrong here? Let's see, no, you're right. Let's see what we got here. So 8, right, so 8, 24, 26 total, yeah. So you and I got to the same number there? Good, sounds good. 2, 4, 6, 8, right? 10, 12, 14, 16, 18, 20, 22, 24, 26. That's okay. I counted wrong too just 5 seconds ago, so we're all good. Okay? So we all got that. Question, why did I put the hydrogen where it is? Why did I put the hydrogen going up? Could I have drawn this?
Yes, but that's not conventional.
Could I have drawn that?
Yep.
Is there any difference in that?
No.
What's the relationship between these two here?
Well, really, they're the same molecule, they're just kind of drawn from a different perspective, right? There's some kind of mathematical symmetry operation, we could say, that relates those two, whether it's an inversion or a mirror or a rotation, right? There's some kind of mathematical operation that we could back out and say, here's the mathematical relationship between those two, okay? And that sounds tedious, right? So we'll just say, right, that there's basically a change in perspective. That's all it really comes down to. In fact, could I have put my hydrogen here? Sure, could I put my hydrogen there? And all of those are the same. And here's kind of where it starts to take a little bit of a, maybe, broadening our perspective, okay? So that molecule there is actually chloroform, is what the name of it is, right?
Ooh.
And if you have a beaker of chloroform sitting on your desk, right, the molecules there are tumbling and moving, right, and moving around in all different directions. They're not all facing the same way, right? Some of them are going to be facing the same way, okay? But they're all going to be moving around anyway, right? What are we trying to do when we draw these structures? Remember, when we draw these structures, it's for us to kind of sit there and analyze the properties and the geometry and where the electrons are and where the positives and where the negatives are, okay? It's just a way for us to represent this. In reality, remember, all molecules are moving around. They're spinning, they're turning, they're bending, they're flexing, they're vibrating, right? There's all these things that's going on with it. So we just take a snapshot of it, okay? So it doesn't really matter where you put that hydrogen in this instance. Now what we're going to talk about when we get to the 5 and the 6 geometry, okay, the geometry of the 5 and 6 things, that it will matter where we put certain things, okay? But for tetrahedron, not going to be an issue. For trigonal planar, not going to be an issue, okay? For linear, not going to be an issue. You guys with me on that? Okay, cool. So last one there, SO2, right? So let's see, we've got sulfur has 6, right? Oxygen has 6, so a total of 6 times 2, right? So a total of 18 electrons, yes. Sulfur goes in the middle, we connect everything. Sorry, I'm kind of getting ahead of myself here. Sulfur connects everything with oxygen, so we got 16 electrons left, right? So 2, 4, 6, 8, 10, 12, 14, 16. Good. Where's my last 2 electrons go?
Sulfur?
The sulfur. Good. Okay.
And that's the form for it?
That's a Lewis structure for it, right?
Is it the one we're aiming for?
How do we know? Right?
Formal charge, oxygen doesn't.
Right? We check our formal charges. Right now, each oxygen has a formal charge of -1. Okay. Our sulfur has a formal charge of
-2.
not -2, +2. Gross. Right? Whenever you guys see a +2 formal charge, what should you guys do? Right? Make sure you have a very good reason to put a +2 formal charge on something. Do we have a good reason here? No. Right? What's up? Yeah, that might be okay. Okay, so let's see what we can do. Let's share some electrons here. So we'll do this. What do we think? What did we do by adding that what did we do by adding that double bond between the sulfur and the oxygen?
We gave sulfur.
Right? So we gave sulfur some access to some more electrons. What's the formal charge on this oxygen?
6.
0, right? 0. What's the formal charge on the sulfur?
+1.
+1. What's the formal charge here?
-1.
-1. Do you guys see what happened as soon as we make a double bond between something here?
But
Right, started at,
You're not supposed to have +1 and -1 next to each other if there's a negative, right? Like,
It's okay to have -1 next to that. It's okay to have a negative next to a positive.
but
You don't
it's
want
not
a
the most
positive
stable.
next to a positive, huh?
But it's not the most stable, right?
Why?
Because it's not symmetrical.
So hang on to that thought. Okay, so take a look, right? We started off with a -1 and a +2. We made a double bond and we decreased the formal charge there for each one of those atoms. Do you guys catch me on this one? Right? So what would happen if we took another double bond from over here? Well, now it's -1 and +1. If we make another double bond, where do we end up? 0 and 0, okay? Is that a valid thing to do?
Sure is.
It sure could be, right? Is there anything odd about this?
Yeah.
What?
Your sulfur is yellow. Doesn't have 8 electrons. It's got 10.
Yeah, so sulfur is violating the octet rule.
But it's allowed to.
It can, right? Is it okay for sulfur to go beyond 8?
Yes.
Sure. Okay. Now, which one's the correct answer? The correct answer is actually somewhere in between these two, is what the real answer is.
How can you have a between form?
Good question. How can we have a between form? What's the relationship between these two Lewis structures?
A bond,
We make a bond, right? We turn a lone pair into a
double.
double bond. Did we move any atoms? No. All we moved are what?
Electron.
Electrons. What's the relationship, or what do we call Lewis structures where we move and make double bonds or turn double bonds into lone pairs? Those are resonance structures. Got it? So when I say both of those exist to some degree, what I'm saying is, hey, this is a resonance structure, okay? So the question then becomes, well, which one is the valid resonance structure or the dominant resonance structure? And the answer is, I don't know. And you guys don't know either, okay? I'd have to give you guys some other information about it, okay? In fact, it's still sort of a area of debate, they might say, right? In some cases, in some papers, in some locations, they'll say this is the dominant form, and some they'll say that's the dominant form, okay? I don't care about that. I'm not asking you to definitively tell me which one it is. Okay, what I did ask you is to tell me what the molecular geometry is for this, okay? Now this is the important part. Does the geometry change in our resonance structures here? That's the question. Now geometry is based off of what? How many total things are around that central atom? You guys with me?
But isn't a double bond still only considered one electron group?
Yeah, it's considered one thing, right? So how many total things do we have around that sulfur? 3 here and
3 there.
3 here. So is our geometry going to change?
No.
No. So what is our geometry going to be?
Little triplanar thing.
You guys do have your notes in front of you. I don't think we're talking about triplanar thingy. Probably not the geometry, right? Right? So we have 3 total things around it. So what's the electron pair geometry going to be? What's the electron pair geometry? No, the electron pair. There's only the 5 big
Trigonal
answers, right?
plane.
Trigonal planar. Got it? If you have 3 things around a central atom, I don't care what those 3 things are, right? The electron pair geometry is trigonal planar, right? So when you guys think trigonal planar, it's kind of exactly what you guys are thinking in your mind, right? It's a triangle, right? Sulfur in the middle. We have our 3 things coming off of it, okay? We've got our lone pair up here. We put our oxygen here. Ooh, we'll draw a better bond there, right?
Why do you have a bond going to the lone pair on sulfur?
I'm just showing you guys how I draw it, right? With a trigonal planar, right, we have 3 things. Why did I arrange them in this shape?
Propulsion theory thing.
Which means what?
The electrons are going to make sure that they're as far away as possible.
Gotcha, right? So we want to make sure we spread things out as far as possible. The other thing that Andy's saying here is what's the idealized geometry in any trigonal planar electron pair geometry?
120 degrees.
There's 120 degrees, right? So the reason why I drew it like this is to kind of represent that we have 120 degrees between everything. You guys with me on this one? Is anything coming out of the plane? No. Is anything going into the plane? No. Can we draw everything in a plane? Yes. Hence the name what? Trigonal planar. You guys got it?
Yes.
Not too bad, right? So now, as was pointed out here, it does look kind of weird to put that bond to the lone pair. And so if we did want to represent that, you could just do it in that fashion, okay? If you guys left the bond there to the lone pair, would I count you wrong? No, okay? We're learning how to draw things, I'm fine with that, okay? But in reality, obviously, there's not a bond to a lone pair, okay? So, the electron pair geometry is trigonal planar. What's our molecular geometry? One lone pair, two atoms. So it's bent, right? Remember, with our molecular geometry, we don't look at our lone pair, we just look at the arrangement of the atoms. Got it? Does that mean the lone pair isn't there? No, that's one of the most common mistakes, okay? The book talks about them being invisible, we say we ignore them. That doesn't mean they aren't there, we're just saying we're looking at the arrangement of the atoms. The arrangement of the atoms is dependent on where the electrons are. They don't magically disappear, okay? So the molecular geometry is bent. The electron pair geometry, though, is trigonal planar. Okay? Fantastic. Good. So any questions about these four examples here? Guys feel comfortable drawing things as a tetrahedron with your wedge and dash?
So anything that has like double bonds is a resonance structure. Or what, can you like define what resonance structure is?
Yeah, so you don't move, all you move are double bonds, right?
Okay.
So lone pairs turn into a double bond, or a double bond turns into a lone pair. But they have to be next door to each other, is kind of what it is. They have to be connected to a central atom. What I mean is this. So if we had some larger structure of carbon atoms. So you don't have to draw this down, I'm just showing as an example, right? Oops. All right, so the double bond here in green versus the double bond here in blue, they aren't attached to the same carbon, so you can't draw resonance structures there, right? So we have to have some atom where we can have double bonds attached to it in multiple ways. So carbonate, nitrate, sulfate, phosphate, you know, a lot of those examples that we kind of talked about, ozone, right? These are things that have resonance structures with them, okay? It's a good question, and there's more to it. And we'll learn more about that in Okay, good, okay, so, right, but so right now what I want you guys to start to look at is how we can turn lone pairs into double bonds and back, okay? Any other questions about these examples? Good. What's the idealized bond angles in tetrahedral?
109.
109.5, right? Okay. All right. So now we're going to kind of continue on and go to our expanded octets, our 5 and our 6, how we can put 5 or 6 things around a central atom. Okay. Oh, sorry, I got a little bit ahead of myself. Sorry, we got one last example here, right? So if I ask you guys to draw the Lewis structure for lactic acid, it'd be pretty complex, right? But there it is. What I could ask you guys to do is say, what's the geometry around each of those atoms in lactic acid, right? Now remember, our rules when we go through and draw our Lewis structure and assign geometries and these kind of things, we always say what? We look at the central atom and then count how many things are around it, right? How many central atoms are here?
3.
A lot, right? What do we really mean when we're saying central atom? We're just saying at each atomic position. Take a look at that atom and how many things are around it. You guys with me on this? So what do I mean? So starting here on the left, how many things are around this carbon?
4.
4. So what's the electron pair geometry of that carbon? Anything with 4 around it has to be what? Tetrahedron. So what does that mean about the idealized bond angles?
100.
It's got to be 109.5. What does the Lewis structure look like though? It all looks like what?
Bonds. A bunch of single bonds.
Well, they are single bonds, that's not incorrect.
They'll have the wedges and then.
Well, hang on, right? What's the angle look like here though? 90. Is it actually 90? No, don't make that mistake, okay? Don't make that mistake. When you draw your Lewis structure, right, you guys, we can ignore our wedges and our dashes. When I'm asking you guys to draw your molecular geometries, make sure you guys have appropriate angles and all that stuff in there. What's up?
I have a little bit of intuition about this, but I'm still curious why the red dot on the far left, why is the hydrogen not straight out?
This one?
Yeah, that is two bonds, linear.
Yeah? Is it?
Yes. Should be.
No.
Invisible electron.
It's tetrahedral.
Right. So hang on to that thought. It's a good observation, right?
It's not tetrahedral, the oxygen next to the hydrogen.
The oxygen has two
So-
lone pairs.
Oh, fridge.
So right here, right? So this is what we're talking about. So how many total things are around that oxygen at the top there? 4. What are all the, so that means it has to be 109.5 degree bond angles there. So the electron pair geometry is tetrahedral. What's the molecular geometry, would we say though? 2 lone
Bent.
pairs, 2 atoms.
Bend.
Would be bent. Got it? Do you guys see what we're doing here? So if I give you some giant complex molecule, I'm going to spend hours drawing DNA for you guys on the next exam, right? And say, give me the geometry around each atom. And you guys will say, pass. I'll just take those 10 points, right? Right? But all you have to do is look at the individual atom, right? And then just count how many things are around it. And then just match that to the appropriate geometry. You guys with me on this one? So when we say central atom, really what we're saying is the atom that you guys are looking at. Okay? The thing that has things around it. Okay?
You wouldn't actually make us do DNA, would you?
No, that'd be a waste of time, right? So this carbon right here, 1, 2, 3 things around it. So that'd be trigonal planar, right? This oxygen, 4 things around it, right? So hopefully you guys can go through and do your bond angles and your geometries for all the different atoms that are in here. Okay? Yeah, it doesn't look too bad. Good. Okay. Do you guys get the point of this though? So if you have a more complex system, you approach it the same way, just do it one step at a time, right? As the saying goes, how do you eat an elephant?
One bite at a time.
One bite at a time, right? So same thing here, okay? So just look at whatever atom it is, count how many things, find your lone pairs, find your atoms, and you guys got it. All right, so now how do we deal with geometries that have 5 and 6 things around it, okay? So I kind of,
We cry.
Nah, it's the same way, right? So I just condensed these 2 slides down together, okay? So on the top here, okay, on the top with 5 things, let me kind of scroll this down so we can see one thing at a time here maybe. So at the top here with 5 things around a central atom, this is our trigonal bipyramidal. So if we have 5 things around a central atom, trigonal bipyramidal is our molecular and our electron pair geometries. Got it? Then as we slowly start to add in lone pairs and swap out atoms, right, we have our different shapes that show up. And we've got a couple slides coming up where I had examples of these, just like we did for the other geometries, okay? So electron pair geometry, this is our dominant geometry here, right? And then we have our subservient geometries to those, okay?
So are you saying that Ant-Man could use a seesaw as a seesaw?
Yeah, that's actually what the shape is. The same thing here for when we have 6 things around. So 6 total things. Octahedral is our molecular and our electron pair geometry. Okay. And then as we swap in, right, lone pairs, square pyramidal, square planar, and T-shaped. Okay. Now our trigonal bipyramidal, our 5, and our 6 are going to take us, or are going to require us mostly to draw wedges and dashes also. And I'll show you guys how to do those, okay? We're going to approach it the same way that we do our tetrahedrons. We learn the generic shape, and then we just fill in whatever else is around it, okay? as with everything, okay, as with all geometries, that's the important idea. Put things as far away from each other as we can. And I'll show you what that means. That's going to become that much more important, especially when we deal in 5 and 6. I'll show you what I mean, okay? Just get it. All right, so looking at 5, okay, so trigonal, whoops, well, that's a slight typo there, but another, if you guys say that, that's fine. All right, so trigonal bipyramidal, okay, seesaw, T-shaped, linear. So what do we see about where we add those lone pairs? Where does the first lone pair go? Well, first of all, okay, looking down here at the bottom, there's 2 places where we fit our atoms. What we call the equatorial plane or the axial plane, okay? The equatorial plane is just like the equator of the world, okay? Runs around the middle part of the molecule, runs around the central part of the planet, okay? If you are in a trigonal bipyramidal geometry and you have to fit lone pairs, your lone pairs are going to go in your equatorial plane. Why? Okay, that's the question. And the answer is this. You guys with me? So remember, we want to, hang on just a second. So remember, we want to minimize our contact between electrons. And putting things 120 degrees apart from each other is about as the best we can do in this geometry. Okay? So when you start to fill in lone pairs in a trigonal bipyramidal geometry, stick it in your equatorial plane, okay? You got a question, Rachel?
No, I was answering the question you were asking, like, why do we?
Got it. Now the question might be, well, wait a minute, right? Wait a minute. If I put my lone pair here, we have interactions between there and there, right? We have 2 90-degree interactions and we have 2 120-degree interactions. As opposed to this. So if we have a central atom, okay? And so we've got our trigonal bipyramidal here, okay? Those are 5 places that we can fit stuff. There'd be the generic shapes that you guys should probably learn how to draw, okay? If I put my lone pair here, okay, what happens? If I put my lone pair here in one of my axial positions, I have 3 90-degree interactions with my nearby electrons. Do you guys see what I mean by that? So I have an interaction here. Ooh. I have an interaction here, right? Interaction with the back, and interaction with the front. You guys with me on that? So 3 90-degree interactions. How many 90-degree interactions do I have here, though? Only what? 2. Those 90-degree interactions are the things to avoid. Got it? That's the reason why.
So we want to avoid 90 degree.
Yep, as much as we can. Those are the worst interactions to make.
Are they just a lot less stable? Because of
There's just a lot of repulsion between lone pairs that are 90 degrees from each other, right? Lone pairs take up a lot of space.
Okay.
Good?
What happens if you have 4 lone pairs?
You just have a linear molecule. I can't think of an example of something like that though.
Okay.
Everybody got what they need to? We got some examples coming up here next. So here's some great examples as a little bit of a practice for you guys if you want to see if you can get to the same answers that I did here. So notice the last problem there. That's kind of unusual. Our good old buddy Xenon, right? Where is Xenon in the periodic table? It is a noble gas. So fluorine is pretty darn reactive. Okay, so we can start to make some noble gas complexes with fluorine. Okay? Now it gets harder to do with something like helium. Okay? But with some of our larger noble gases, they do start to react. Okay?
So xenon, despite the fact that it's a noble gas, can sustain 10 electrons.
Mm-hmm.
But aren't noble gases supposed to be the ones that just like always sit happy right at 8?
Guess I lied to you. Sorry.
You forever lost my
I
trust.
know, what can I say? Okay. So if we were to try and draw these on our own, right, if we were trying to draw our PF5 here, okay, what I do, zoom in to give myself some space, okay. The way I draw this, put my phosphorus in the middle, line up, line down, line to the right, okay. And then do my wedge and dash coming out. Okay, so there's my generic shape for my trigonal bipyramidal. Just like we learned our generic shape for our tetrahedron. Got it? Then just fill in whatever you have. And don't forget your lone pairs. Good. Same thing here. Sulfur, up, down, right. Wedge and dash.
Okay,
Goes in.
okay, thank you.
Fluorine, fluorine, fluorine. Lone pair goes into your equatorial plane. Typically, for what it's worth, if it's me drawing something and I have to put a single lone pair, I usually put my lone pair there because it's kind of the easiest one to draw, right? Doesn't matter. What's the relationship between these?
They're the same.
They're the same. Okay, so it's basically just rotating this molecule around. Got it?
It wouldn't be a functional seesaw though.
No, it's a little bit too small for that, yeah. But, yeah,
So like, are we supposed to draw the, dash and wedge, just a lone pair, or can we just put it next to it?
you can just put it right next to it, right?
Okay.
Either way's fine. But I'm just kind of trying to show you guys a three-dimensional shape for it, right? What was I gonna say? Oh, I forgot, but that's okay.
You know what would be really awful? If someone took a Dalmatian and bleached its spots off and then redrew spots in like molecular.
Let's keep our discussion focused. All right, so moving on to octahedral. Yeah, sorry, what's up, Andy?
Back like the force model and stuff, we talked about how much energy it takes to like bring it out of its quantum number and stuff. we're talking about.
Yeah, individual electrons around an atom, yes.
Noble gas.
Yeah.
To get it out of there, does that just mean it has to have a lot of energy in that molecule, or?
So the question that was asked is why in the world, or to summarize this a second, why in the world can a noble gas react even, right? I'll just clear this up here a second. Let me offer a concise explanation for a complex idea, okay? It is really, 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 really difficult to make the same fluorine compound with neon. It is relatively easy to do with xenon. So what's the difference, right? What changes as we go down?
Size?
Our radius, okay? So xenon is a massive molecule, right? It is a pretty large atom. That means that the outside electrons, the outside electrons, the things that are getting added or removed or changed or affected or reacted, they're not held nearly as tightly as they are with neon, right? And so it's still difficult, right? But it can still happen, right? The larger the atom, the more we can kind of deviate from that idea of, hey, a noble gas won't react, okay? The same applies for something like fluorine reacting versus iodine also.
Yeah,
Okay.
okay.
The further away from the nucleus, the more things deviate. Okay, so here's our octahedrons. Here's how we fill in our lone pairs, okay? Notice that all angles in an octahedron are 90 degrees, okay? So can we minimize any of our lone pair interactions for our first entry here? Well, no, everything's still got to be 90 degrees. So why did I put the lone pair here at the bottom? Could I put it on the top? Sure. Could I put it on the left? Sure. Could I put it on the right? It doesn't matter where you put the first lone pair, okay? This is not like our trigonal bipyramidal. I don't care where you guys put the first lone pair. The second lone pair is always going to come in 180 degrees from the first one, though. Got it? That one's going to matter. You guys with me? So, here's some examples for that. Right, SF6, kind of your quintessential example. Actually, SF6 is really, really cool. So SF6 is actually a gas. So there used to be some chemistry demos that we did. SF6 is an extremely dense gas. It's denser than air. And so what you can do is you get a tank of it, you can actually fill up like an empty aquarium, and you can float little aluminum foil boats on top of just this SF6 gas. It's super, super, super cool.
Why
right?
do
So
we
if you
not
got
do this anymore?
why? Well, it doesn't teach you guys anything. Like, it looks cool, right? But there's no like idea behind it, right? So
Density is an idea.
well, it is. You're absolutely true with that, right? But you can look it up online, right? There's plenty of demos with this also. Right? But one of the funny tricks that we used to do is, so you guys have ever inhaled a balloon of helium, right?
My mom got me a helium tank for my birthday one year, and my friend Jake and I would just spend the entire afternoon just inhaling it and singing the Munchkin song.
All right.
It was a great birthday.
A tank of helium. But anyway, so if you guys inhale helium, right, your voice gets squeaky. Why?
Because it's less dense.
It's less dense, right? So our vocal cords are designed in a way to, speak the voice, so to speak, when we have the proper density of air. Okay, so if it's less dense than air, like helium, right, then when it goes through there, it moves faster, it gets squeakier, right, that kind of thing. So if you inhale SF6, okay, it's actually the exact opposite, right? So instead of getting squeakier, you kind of go down a couple of octaves there. But the problem is that it's more dense than air. So if you inhale this stuff and it goes into your lungs, how are you going to get it out?
By hanging upside down.
That's exactly what you have to do. You basically have to do a headstand, right, and take a couple of breaths. So.
I know what we're doing this weekend.
No, you're not. Okay. No, it's not your birthday. No tanks of gases for you. Okay? So,
Wait, even like a vacuum? Because isn't that what happens when you breathe out? Or when you breathe in, you just like.
yeah, I mean, of course, you're not gonna like die if you do it right, but it's the way to make sure you get everything out is basically do a headstand, right? So, yeah. So anyway, I like to tell you guys about that kind of stuff apparently. So need a little bit of a break, okay? But anyway, so here's how we draw our octahedrons. There are two ways of drawing octahedral geometries. I'll show you guys what I mean with that. So here's our every time, right? There are two ways that I've seen it represented. So here's typically what you see in the books. Okay, here's our generic octahedron, right? Where we have the atoms that we swap in. Okay? The other way that you see it represented sometimes is like this. Okay? What's the difference between those two?
Perspective.
Yeah, it's just a perspective, right? It's just a 45-degree rotation is all it is. Okay? Which one is correct?
Both.
Both. Which one can you guys draw?
Either.
Either. Which one's easier to draw? That depends on what you guys want, right? This is the way that I learn, so whenever you guys see me draw octahedrons, I always do it that way. I just find it easier because I have 4 things in the same plane. I don't have to draw as many wedge and dash things. Does that mean it's the best way? Of course it does, because that's the way I do it, right? So everything I do is the best. Got it? All right, so either one of those is fine. That's your generic shape for you guys to go through and practice for your octahedrons or your trigonal bipyramidals, okay? Okay, so there, end of idea. Okay, so there are geometries 1 through 6, right? Linear, trigonal, planar, tetrahedral, trigonal bipyramidal, octahedral, okay? Know how to draw them. Know how to draw your wedges and dashes, okay? Know where your lone pairs go, especially when you get to your 5s and your 6s, okay? And remember that the idea behind it all is that or the reason why things adopt these geometries to begin with are because they're going to minimize the repulsion between electrons, okay? You guys got the main ideas there? Know the geometries, know the names, know the angles, know why they adopt those angles. Good? All right. Let's talk a little bit about bonds. Where we're going to build into is this idea of how do we know if a molecule is polar or not. Okay? And then we're going to say, well, if we know that they're polar, how do molecules talk to each other? So there's 2 big ideas that we have left. Polarity, and then learning how molecules communicate with each other. Okay? So the idea is this, okay? Bond length is directly related to the size of the individual atoms. That's not that much of a shocker for you guys, okay?
Yes, it is. My world is shattered.
Yeah. So the idea is this. So I want you guys to think here for just a second. What are we measuring, right? What are we measuring when we're quoting the radius of an atom? We're measuring from the from the middle of the atom, right? From the middle of the nucleus to the outermost electron in the shell. Got it?
Yep.
What quantum number affects the size of our atoms? What quantum number affects the size of our atoms?
N?
N, our principal quantum number, right? Remember what we said about our principal quantum number N. It says as it gets bigger, right? 1, 2, 3, 4, 5, 6, 7, right? It means that our orbitals get bigger. You guys with me on this?
Yes.
Okay. If our orbitals get bigger, what does that mean? Well, our orbitals are where the electrons live. How do we make things, or let me ask this, let me figure out a better way of asking this. What makes a bond? A bond is when our orbitals overlap with each other. Got it? So if we have a big orbital overlapping with a big orbital, guess what we get? a big bond. Garbage in, garbage out, right? That's the rule of life. What you put in is what you get out. So if you put two big orbitals together, guess what you're going to get? A big bond. If you put two small orbitals together, what are you going to get? A small bond. Does that make sense? So if you have two big atoms that you bring together, you're going to have a long bond distance. If you have two small atoms, you're going to have a small bond distance. That's all it is. Okay? So that's what we're talking about up here at the top, right? Just based off the radius, we can kind of predict what the bond lengths are going to be for those, for these two atoms coming together, nitrogen and carbon and phosphorus here. But take a look down here, right? So as we go from single to double to triple, okay? As we go from single to double to triple, right? We start to decrease the bond length. So the more glue that you put in between the atoms, the more electrons that they share, okay? The more glue that you put in between atoms, the harder, that's the next idea, excuse me. So what I mean is the more bonds you put in between atoms, the shorter that distance becomes, okay? The tighter they are held together, okay? So radius of the atom, and whether it's single, double, or triple, those are the two things to pay attention to if I ask the question of which is going to have a longer bond, okay? Look at the radius, and look at look at your Lewis structure to check for single, double, or triple bonds. Got it? How do we know the radius of an atom, relatively speaking?
Periodic table.
Take a look at the periodic table, right? Take a look at your quantum numbers, that kind of thing. Good? So this is just a table, you guys have it in your book, you know that it probably looks different at this point, okay? But this is just telling us the bond length of certain combinations of atoms. Obviously, I don't expect you guys to know the specific numbers, okay? What I would expect you guys to do is give me the relative difference in between something, right? So if I say, hey, here's this pair of atoms and here's this pair of atoms, which one's going to have a longer bond? You would take a look at your radius, right? The bigger the atoms, the longer the bond. That's all it comes down to.
Hey Doc, am I stupid or is there not bond radius, or is there not radius on this table?
Probably is, I don't know.
Are those numbers?
I'd be surprised if they put it at the front like that. It's probably in the back somewhere. Okay. Now, why do we care about the length of the bond? Well, here's what it comes down to. The shorter the bond, okay, I'll go ahead and give you the punch at the beginning here, right? The shorter the bond, the harder it is to break that bond, okay? So if you remember way back in chapter 5, okay, where we're dealing with enthalpies, we're talking about where energy goes to or where it comes from, right? What happens in a combustion, these kind of things. That all just comes down to a measure of how strong or how weak the bonds are, okay? If I want to rip two atoms apart, I have to put energy into that system to break those atoms apart. The tighter that bond, the shorter that bond, the more energy I have to put into it. That's what it comes down to. The bigger the bond, okay, the longer the bond, the easier it is to pull those atoms apart, okay? And so we get into this idea of bond enthalpy, right? And so the third bullet point there, right, the amount of energy in the gaseous state that it takes to break 1 mole of a bond in a compound is the bond enthalpy, okay? That's what we're talking about. So this is how much energy it takes to break a bond. That's all it's talking about, okay? And so here's just kind of an idea with that, right? Single, double, triple bond. Triple bond takes almost 900 kilojoules. I know. What, 900 kilojoules? Oh man, I thought it was going to be 700, but that's crazy. 900, oh, okay. Again, I don't care about the numbers, right? Just care that each one of those is going to take more energy, right? Single versus double versus triple. Takes more energy to break a triple bond. It's a shorter bond, okay? The same thing goes for carbon to carbon, carbon to nitrogen, doesn't matter, In general, the shorter the covalent bond, the stronger it is, or the more energy it takes to break apart, whatever you want to fill in that blank here, okay? But you have to be comparing similar types of bonds, okay? I have to give you some kind of information to be able to make a statement like this. Because there are actually other factors that affect bond strength. It's not just purely dependent on the radius. There's other things too, okay? But within a series, right, within a series, you guys should be able to explain to me why, right, the bond enthalpy for bromine to fluorine is higher than it is from bromine to bromine. Why would that be? Fluorine's a smaller atom, right? So it'd make a smaller bond to bromine. If you have a smaller bond, then it's going to take more energy to break that bond, right? That's the explanation that we're thinking about. Does that make sense? And there's kind of the two ideas there. Bonds get weaker as they go down the column because radius gets larger, right? And bonds get stronger as they go across the period, right? Because atoms get smaller. Yeah.
Which way affects it more?
Huh?
Which way affects it more? So like if I have something, it's an atom connected with atom A and the
Yeah, you're talking about whether it's up or down, left or right.
Yeah.
Yeah, up or down.
No, I mean like,
Oh, I'm sorry.
because I thought you said that it has to do with size and
Yep.
also, does it not have anything to do with electronegativity at all?
It does.
Okay.
There is that impact. That's so my statement that I just made is there are other factors at play here, right? But in general, right, we can estimate it based off of the radius itself, given a specific series here, right? If you notice, I'm keeping bromine constant in all of these, right? I have to keep one thing constant. I couldn't have thrown something like, oh, this is a chlorine fluorine versus bromine chlorine, right? You can't really do things like that, right? Because there is something else going on.
Okay. Thank you.
Mm-hmm. Another table, right, we've just given you guys the enthalpies for specific reactions. There are a couple examples in the book where you guys will have to look up your bond enthalpies, okay, to figure out what the actual number is. And so those bond enthalpies are either given as part of the problem or they're in the back tables of the book, okay? So how in the world do we put these numbers together? Well, there we got our familiar delta H, right? Whenever you guys see a capital H in chemistry, it only means two things, right? Either hydrogen, right? Not the case here, right? Or if it's italicized, right, we're talking about enthalpy, okay? So the change in enthalpy, here's what it comes down to. The sum of the bonds broken minus the sum of the bonds formed. How do you know how many bonds are broken in a reaction? And how do you know how many bonds are formed in a reaction? We'll take a look at the problem that we have here. CH4 plus 2O2 goes to make CO2, right? Plus 2H2O. A simple combustion reaction, right? We're burning natural gas. We're burning some methane. How do I know how many bonds are broken? How do I know how many bonds are made? Well, let me ask you a question. How many bonds are there in CH4?
4.
4. How do you know?
H4.
Give me a better reason.
Because there's gonna
Lewis
be.
structure.
The Lewis structure. You guys got it? So what do I mean when I'm saying bonds broken and bonds made? You have to know what those bonds are based off of drawing the Lewis structure. Got it? Because we have to know whether we're dealing with single or double or triple bonds. Now CH4, as we know, has only 4 bonds and they're all single. Because that's how hydrogen works. Got it?
So would double and triple bonds still be counted as one bond?
Nope. They're counted as one double bond, right? Or one triple bond, yes. But not a single bond.
Okay. So let's say that H2O,
Is this another Dalmatian question?
no,
Oh, okay.
let's say that H2O had double bonds between the oxygen and hydrogens. I know it doesn't,
Mm-hmm.
but if it did, okay, yeah, 2O2. Okay, so the double bond in 2O2 there,
Mm-hmm.
are we gonna say that that's like 2 bonds broken per atom?
We are breaking a double bond.
So are we counting that as one bond broken or two bonds?
How many of those do we have?
We have two.
Two of them,
So
right?
we're gonna say it's two bonds broken rather than four?
We're breaking two double bonds.
Okay, so 2 or 4 bonds broken.
Two double bonds.
That's the
A double bond is a thing.
Are double bonds counted differently in the sum of bonds broken than single bonds?
They are still considered a set of bonds that have to be broken.
Okay, but only one set,
Yes.
okay.
Okay? So, to answer a question like, oh, sorry, you had a question?
Oh, no.
Oh. So to answer a question like this, the first thing you need to do is draw your Lewis structures so that you know which bonds are going to be broken and made. Got it? The next assumption we make is that you break every bond, right? You break every bond in your reactants and you make every bond in your products. So break everything, make everything. You guys see what I mean by this? So what I mean is I'm going to break all 4 of my CH bonds. Okay? That's just the assumption we work with. I'm going to break both of my oxygen-oxygen double bonds. Don't forget our balanced reaction, our stoichiometry. Okay? I'm going to make, right? I'm going to make 2 carbon-oxygen double bonds. Do you guys see where I'm getting the 2 from there? It's not the stoichiometry in this case, it's just I have 2 sets of those double bonds. You guys with me on that? Okay? And I have 4 oxygen-hydrogen bonds. Why 4? Stoichiometry of 2 there. So break everything, make everything. You guys with me? Then all you gotta do is look up the values for those individual bonds in your book, and you just plug in your numbers. Okay?
So that 498, is that the value for a double bond?
Yes, an oxygen-oxygen double bond. Yep.
How do you get 4 bonds in the last one with the H2O?
Right, so we have 2 OH bonds
Yeah.
per 1 water.
Oh.
And there's 2 waters in there, right? Good question. Yep,
Maybe just multiply that by the enthalpy, bond of
Yep.
enthalpy. Okay.
that's it. Break everything, make everything.
You got the break it down.
Right, so remember when we ask this type of question, now draw your Lewis structure first, see whether you have double or single or triple bonds in there, and then look up the appropriate values. The easy thing to miss is that you guys say, oh, everything's a single bond, and you just pull that value in there. And then you're gonna get it wrong, okay? So draw your proper Lewis structure, just what you've been doing all along, and make sure you guys pull in the right values. Okay? Not too scary, right?
I'm shaking.
I've stunned them into silence, just like I like to leave my audience. Okay, so it seems like a good place to stop. We'll pick it up on the next stuff there on Wednesday. I will be, excuse me, I will be posting a quiz for you guys here soon. It's going to be on drawing Lewis structures and that kind of stuff. Okay, so take a look for it online, and I'll give you guys, pretty much that whole day to get it done. But make sure you guys get it done. All right? No, not today. It'll be sometime later on this week, probably Wednesday or probably Wednesday or Thursday or Friday or something like that. Okay? So just keep an eye out for it. I'll post an announcement as soon as it goes up. All right?